Hello folks, it's Professor Fiore, and in this video we are going to be talking about DC offset in op amps. What's a DC offset? Well, basically it's a DC output voltage, an undesired signal, a DC signal, and this will create an ambiguity, in other words, an uncertainty in the true DC output signal. So if you were measuring a DC signal from a sensor, and you get an output voltage, and just to throw a number out, let's say it's 100 millivolts, a portion of that is not really from the signal, it's really a DC offset created by the op amp itself. So, things we want to look at in this video. The parameters that make up the DC offset, how we can measure it, calculate it, simulate it. Those parameters are called VOS, the input offset voltage, and IOS, the input offset current. Some data sheets list those as VIO and IIO. Same thing. The thing we want to consider is the noise gain of the amplifier. As we'll see, the higher the noise gain of the amplifier, the worse the offset's going to be. We want to look at the effect of resistor size. And one of the big things I want to do here is talk about simulator issues, because there are certain sorts of gotchas, if you will, when you simulate DC offset that you would not see in the lab. And this is really important. We're going to take a dive into that. First, let's take a look at a typical non-inverting op amp, see what we get. So what I've got here is a 741, RF 990K, RI is 10K, so the gain, RF over RI plus 1, right? So it's 990K over 10K. I just chose those numbers so I get a nice round gain of 100. Now notice what I've used for my input. I've got a 10 millivolt sine wave, 10 millivolt peak sine wave. So that's going to get multiplied by a gain of 100. I should get a 1 volt peak output. Right? Why use crazy numbers when you can use easy numbers that you can figure out in your head? And then there's, along with it, a positive 10 millivolt DC signal. So that is also going to get multiplied by 100. Remember, the op amp here has no lead networks. Frequency response goes down to DC. So that 10 millivolts gets multiplied by 100, 1 volt DC. So I've got a 1 volt peak sine wave riding on a 1 volt DC signal. So this sine wave should produce a positive peak at 2 volts and a negative peak at 0. If everything is working perfectly, that's what we should see at V load. So let's do a transient analysis. All right, so here's our sine wave. And you can see, well, it's not going from 0 to 2. This whole thing has been shifted up. All right, you can see this much. We've got a couple tenths of a volt out here, right? Each one of these hash marks is a tenth. So we've got, not quite, but about 2/10 of a volt. This thing has been pushed north, so to speak, right? That's the DC offset we're talking about. It's generated by the op amp. Not so good. We don't like that, all right? Okay, just so that we can remember, I'm going to put a little note on here. This is original. Okay, beautiful. Now, how do we determine on a piece of paper, right? I mean, in the lab, we'll just go in and measure this. But how do we determine, what this is? What are the contributions that go into this DC offset? Well, let's take a simplified example over here. So I got rid of the power supplies and all that, right? So just sort of a blocky kind of diagram. We've got our feedback resistors. The input signal, we're just going to short back because I'm looking at the DC bias on this. It turns out that there are sort of two parts that contribute to the output offset. One is from the VOS, the input offset voltage, and that's due to slight mismatches between the differential amplifier transistors, right? Are the VBEs identical? No, they're not. So that's going to create a small DC offset at the input. Ultimately, that gets multiplied by the noise gain of the amplifier and produces a portion of the output, right? So VOS times the noise gain. And in this circuit we were just looking at, the noise gain and the signal gain, of course, are the same. The second part of of this is the input bias current. So the bases, right, the bases of that pair of transistors in the diff amp, they're pulling current or pushing current, depending on whether they're NPNs or PNPs, but there are bias currents coming in or out of these inverting and non-inverting inputs. Now, we can see that the plus input is tied right to ground, but the minus input, there are a couple of resistors out here, and that bias current is going to pass through these resistors and ultimately is going to create a DC voltage, right? DC bias current times these resistors gives us a DC voltage at this point here, at V minus, the inverting input of the op amp, okay? So that differential voltage, in other words, whatever the voltage is between V plus and V minus on the input, because of the bias currents, that also gets multiplied by noise gain and becomes the second part of the output, right? So those two things together, the VOS contribution and the bias current contribution. So the V plus is 0, like I said, it's grounded. The V minus would be the bias current coming in on the minus, right, times these two resistors in parallel, right? That's basically what it works out to. So, we can expand that out. It's, product sum rule, right? Ri times Rf over Ri plus Rf times the I bias. And, V plus is 0, so you can just say it's 0 minus that. And when we talk about offsets, we normally talk about magnitudes. We don't really care about plus or minus because those are both possible, right? So for example, when you look up VOS on a data sheet, they'll give you a typical value, like they might say it's 4 millivolts, and then they'll give you a maximum, a worst case value, 5 millivolts. They'll never give you a minimum value because the minimum would be 0. In other words, you just happen to be really, really lucky. But when they say something like the typical value is 4 millivolts, that is irrespective of the polarity. In other words, it could be plus, it could be minus. So when we talk about a maximum, like they say a maximum of 5 millivolts, they're really saying that the VOS value can be anywhere between plus 5 millivolts and minus 5 millivolts. So it could be 5 millivolts, it could be 0, if you're really lucky. It could be, minus 4.3 millivolts, could be minus 0.2 millivolts, could be plus 1.37 millivolts. You just don't know. Same thing is true with the input current offset. We don't know what the bias currents are precisely, right? These two bias currents coming in here, well, do you think they're going to be identical? No. I mean, even if the emitter currents were identical, the betas for the two transistors most likely are not. So the base currents, in other words, the input bias currents, are going to be slightly different. That's going to produce a little bit of an offset. So, which transistor has the higher beta? I don't know. Luck of the draw, right? So, the current coming into the plus might be higher than the current coming into the minus. Just as possible the other way around. And it's this unknowing that leads us to the ambiguity. So all we can really do here is compute, well, how bad is this, right? So, these two parts that we would compute, we automatically assume that they're both off in the same direction. Now, it might turn out in a particular op amp that that's not the case. One of them might be negative and one of them might be positive, meaning that they partially cancel. You can't depend on that, though. So when we're doing an analysis, we just use the magnitudes and we just assume that they're both off in the same direction, right? I don't want to make an assumption of things working out to my advantage when they might not, all right? So in any case, looking at this, if you consider for just a moment, if we added a resistor back here, right, instead of having 0 minus this quantity, if I added a resistor back here, there would be a bias current flowing through here. And if it just so happened that the two base currents were the same, and I set the right resistance value here, then we could get a 0 voltage for the differential. In other words, we'll develop a voltage across this resistor. We've got the voltage across this resistor, and if they happen to work out to the same number, we have a nice improvement, all right? In other words, something like this. So I add this offset resistor, right? So on the plus input, basically we have the non-inverting bias current, that base current, times this R offset, okay? That produces a voltage out here. And then we have the other one on the other side that we just looked at a moment ago, right? The negative inverting input bias current, right, that base current, times the parallel combo of Ri and RF, all right? So we wind up with this little equation here, right? I bias plus times R off, that gives us this voltage. And then I bias minus times the parallel combo, that gives us this voltage. We subtract them, that's the input offset voltage. So if we set R off to the parallel combo of Ri and RF, these things can cancel. And in other words, the contribution from the bias currents is nil, right? But as I said a moment ago, what are the chances of the two base currents being identical? Pretty stinking small. So what we really have is the differential between the two, and that's what IOS is. IOS is the input offset current. It's the difference between those two base biasing currents. So you can think of one of these things as fixed, and then the other one being that same value plus IOS, right? In reality, it's plus or minus IOS. But again, we just think in terms of the magnitudes here, all right? So we set the resistors up so R off is equal to Ri in parallel with RF, okay? Now, that turns out to produce this offset voltage that's IOS times R off times the noise gain, right? Because that differential, like you could think that, you know, whatever I get here, that voltage is the same as what I get here. And then there's this extra little bit due to IOS. So, you know, it's IOS times the resistor. And of course, this parallel combo is that value. So it doesn't matter which way you want to think of that. But that gives us a little voltage. We multiply that by the noise gain. That gives us the second piece. Okay. Now, this is where things get a little bit simpler. R off is the parallel combo. In other words, is using the product sum rule, Ri RF over Ri plus RF. The noise gain can be written as either 1 plus RF over Ri or as Ri plus RF over Ri. It's the same thing. But when you look at this, see the Ri plus RF, they cancel. And then the Ri cancels. And what you're left with is IOS times RF. Beauty. I love the simplicity of that. It's nice when things work out conveniently, right? So the total output offset would be the VOS piece, in other words, VOS times the noise gain, plus IOS, the input offset current, times RF, right? That's the total. Those are your two pieces, right? So to make a minimal value, right, the smallest possible value for statistically, right, because it's going to vary from device to device, but you know, to head toward that best case thing, what we do is two things. Right? First, we add the R off, okay? And then secondly, we try to make the feedback resistors small. Now, even if that didn't have an effect on the DC offset, it's good to make the resistor small because it has a positive effect on noise. The smaller the resistors are, the smaller the noise will be. So there's a second good reason to do that, even if you didn't have this advantage. All right, so let's go and look at a modification of our original circuit. So what I've done is I've simply added the R off resistor here. All right. Okay. Oh, and by the way, if you're thinking about noise, yes, this does add noise. All right. There are some techniques you can do like bypassing this to get rid of that. And sometimes, you know, you don't really care about the DC offset, or, you know, you're just primarily doing an AC thing, in which case, hey, if you got a DC offset, you could just put a coupling cap out here, right? Ignore it. But sometimes we do wideband stuff that includes DC. So I want to bring up both of these things. In any case, let's do that transient analysis one more time. Okay, now this is circuit number 2. So let me put a little text box up here. Okay. Just so I don't forget. All right. Now let's go back. So this still has some offset in it. All right. This is, again, this should go from 0 to 2. And it does look like it's still a little bit off. So it's better than the original. All right. I can just flip back and forth between those. The offset on here still exists, but it's better than what we had. Okay. Before I go any further, let me just say, if after all of this you can't get the offset low enough, it's time to go look at a new op amp. You're going to have to find an op amp that has lower values for VOS and IOS. Fortunately, nowadays, the latest generation of op amps, wow, the values are really small compared to what we had to deal with, 30, 40 years ago, right? It's amazing what's transpired in that time. Okay, so that's sort of like part one, if you will. The second thing is, what about keeping the resistors low? So here's the same circuit once again, right? So here we've got the IOS effect reduced, hopefully, by lowering the resistor values. I still have the gain of 100, right? I just chopped everything down, right? I had 990K here, so I just dropped it down by a factor of 100 for these resistors, right? So our formula says we should get even less offset here. Okay, so let's do the transient analysis one more time. Hey, didn't you say that last time? And before I forget, I'll put this down as circuit 3, because we are going to be flipping back and forth between these. So I don't want to lose track. All right, so again, this still has an offset. Let me go back to the circuit number 2 that still had the big resistors. Hey, that actually has less offset. Right? This is the one that's supposed to be better, and the offset is in fact worse. What the heck is going on? Here's the original. So that's terrible. I mean, both of these things improve, but it seems like, keeping the resistors small isn't working. What's the deal here, man? Hey, professor, you lying to me? No, I'm not. There's a good reason. What is that reason? Well, this goes back to the simulator itself. If you built these circuits in lab, like you got 10 op amps, right? You got 10 741s. You build up these circuits, every single one's going to have a different offset. Some of them are going to be positive, some of them are going to be negative, some are going to be pretty small, some are going to be a little bit bigger. Because again, we don't really know what the matching is. They, meaning the manufacturer, can only give us a range. They can only tell us, hey, it's going to be around here. Worst case, it's going to be this much. But somewhere in there is where it lies. It's a statistical occurrence. It's a probability in terms of what you're going to get. So, like I said, sometimes the iOS bit and the VOS bit partially cancel. What's happening here? Okay? The values for VOS and iOS are fixed in these amplifiers. They don't change. You run this simulation 20 times, you're going to get the same offset 20 times. That's not what happens in the real world with 20 different op amps. You're going to get unique values for each one. All right? So I'm going to go back to circuit number 2, and we're going to do a little mod on this. I'm going to go into the 741 and actually look at the spec values. All right? So you can see the input offset voltage is spec'd at 1 millivolt. The bias current is 80 nanoamps, but the offset current right here, input offset current, that's iOS. So what I am going to do is I'm going to turn that into a negative value. So it's a 50-50 proposition that for any specific op amp, that's a positive versus a negative value. Now, it just may be that with these two positive polarities, these things actually fight each other. It all depends on how the model is built internally, okay? So let's just try this. All right, so this is circuit number 2 with our little mod. Let's see what we get. Oh, that looked like it went up. And so I don't forget. So this is circuit 2 with negative iOS. Okay. So let's go back to the original circuit number 2, which I think was this one. Yep, there's circuit 2. So, hey, look, it's worse, right? Because back here, those two things were partially canceling. Over here, right, they're going off in the same direction, so that's worse. And I can look and say, yeah, look, dropping the resistor down is actually better than that case, right? So sometimes it'll actually work out, right, that the bigger resistor will actually give you a lower offset. But you're kind of like playing Russian roulette there, not necessarily the case. And, what will happen if I do the same thing over here, right? Is this going to go the other way? Well, let's find out. So this is circuit number 3. Again, with a flipped polarity on the input offset. By the way, you could do the same thing. You get a similar effect if you swap the VOS polarity. Okay. In this particular circuit, the VOS piece is bigger than the iOS piece. You could, and I really strongly recommend, you take some of these little experiments on your own, futz around with these values. Instead of getting a positive offset, you could just as likely get a negative offset. All right. So it's a good thing. It's good to understand how your tools work, what they're good for, and what their limitations are. That's really important. Okay, so in any case, let's run the analysis on this as he chatters away. All right, so this is circuit 3 with the mod. All right, so I think this was the circuit 3 without the mod. Right. All right, so, there's no change. There's no real change. And that tells you something very important. What it tells you is that the contribution, iOS times RF, is orders of magnitude smaller than the first contribution, VOS times A noise. So at this point, we've made the resistor small enough that it's never going to make it worse, right? The DC offset's never going to be worse is because of this. Whereas, when we sort of monkeyed around with like circuit 2, okay, it could get worse. So this constrains just how bad things can be. Now, like I said, it's possible, it's all possible, luck of the draw, that you could get something better with a bigger resistor because of the partial cancellation. But, again, that's a bit of a crapshoot. So that's the way it works out. As a matter of fact, in many circuits, when you have small resistors, you could just approximate your DC offset as noise gain times VOS. Okay? The higher the gain, the worse the DC offset. And that's just the way it is. Now you might think, hey, what if I just make my circuits have small gains? Well, that's not really a solution because then your input signal doesn't get much gain either. And ultimately, you apply gain to get the signal out as big as you need it. So you're kind of constrained there. All right. Matter of fact, to compare amplifiers on an even keel, what we sometimes do is we compute what's called input referred offset. And what we do is we take the output voltage, the offset voltage, and we divide it by the signal gain of the amplifier. That way, the value that we get, we can compare from amplifier to amplifier if those amplifiers have different gains. All right. So that's an even way to do it. Otherwise, high gain circuits always appear to be, worse just because the gain is so high. All right. So, like I said, if you ran 20 versions of this, you're always going to get the same result because the op amp doesn't change. Some simulators have the ability, right? It's generally called a Monte Carlo analysis. They have the ability for you to assign percentages to parameters like resistors or device parameters, like in this case, the iOS. And then you could run, a dozen or however many simulations. And every time it does a simulation, it'll slightly alter that, right? It'll do a little randomization within the percentage that you specified. And that would echo what happens in the real world, right? So don't get into the thought you do a simulation, you get a specific answer, right? Oh, I get, 6 millivolts of offset, or I get 112 millivolts of offset. That's what it's going to be. No, that's not what it's going to be. Not in the real world, because those parameters are going to change. Every time you do it, you're going to get a different result. You get a different op amp, different iOS, different VOS, off you go. All right. So bottom line, when we get back to this whole thing, you want to keep your resistors small. You want to include the R offset. If you still can't get it low enough, if you still can't get the DC offset low enough, it's time to go look for a new op amp. Okay? All righty. Hope you enjoyed this one. See you next time.